Hi, my name is Chuan. So today I'll be presenting about my project, which is modeling and structural analysis of a small-scale solid rocket motor stand. So without further delay, let's start my presentation. So this is my presentation agenda, which is I will starting with introduction and overview, followed by methodology, results and discussion, and then lastly conclusion. So first comes first. A solid rocket motor requires rigorous testing prior to operational usage. It is important to have a reasonable consideration and other logical elements which accounts to reliability and feasibility. So the things that are mainly here are the configuration for unit under test, instrumentation and measurement, and the accuracy and precision of the data acquisition. So a scaled down testing is actually a more cost-effective solution. The most common testing is the static fire ground test, which is to assess the performance through various parameters. This system is known as Thrust Measurement System. Under this TMS, there are a few structures which are the mechanical test structure, electrical assembly, and also the data acquisition system. To be clear, the scope of this study involves the design and analysis of the test structure for the static ground test. All in all, they are to ascertain the confidence level of these metrics where to ensure design requirements are met. So here are the design requirements. First is the simplicity for the years of construction. Next is to able to accommodate different classes of the solid rocket motor. Last is the flexibility for the equipment integration where different instrumentation can be exchanged. After reviewing different types of test structure as seen on the right, which is the deformable rectangle type and the mobile L-block type, few design drivers are listed, which includes the principles of instrument design, measurement uncertainty, and the dynamic response of the test structure. The vertical test structure is eliminated as it is more likely to be subjected to lateral oscillations, and therefore horizontal test structure is chosen. The L-block blades are more stable application as it can reduce lateral loadings as well, while the deformable rectangle type will be subjected to more noise during data acquisition. And so, the final design chosen is the horizontal L-block stand. And also, our design features the variable fixture mount along with the variable instrument design. This is to cater the customizability to test a variety of SRM, while the instrument design can accommodate higher range and sensitivity of load cell, with an enclosure and alignment mechanism in effort to reduce errors in measurements. Next is the model of our design. From here, this is the 3D model of the complete test stand assembly, which includes the truss adapter, the base plate, and also the rollers as well as the mounts. The dimensions of the test stand are as shown, and the design is compatible for a diameter range of 28 to 99 mm. The loading frame and the truss adapter are to be analyzed, where the truss adapter will be the elastic element of the load cell and is hypertized to experience minimal deflection. Analysis will be done to evaluate the structural integrity of the test structure. The analysis is done to evaluate the stress magnitude and also the load distribution on the test structure. As the truss adapter consists of the cap and the circular hollow section, uniform static load will be set as the truss loading. Typically, the finite element analysis will be done to analyze the structure. Around 85K of parabolic tetrahedral elements will be used. For the material selection, the load cell and the fasteners will be using AISI 316, while three materials will be chosen for the frame and the truss adapter to be analyzed. Next is the assumption made for the analysis. From here, we can see that the inertia and damping forces are ignored, while the bottom base plate is used as a fixed support, followed by gravitational effects that will be included for the analysis. It is important to take note on the contact type used for different analysis. For the linear static analysis, the no penetration contact is used as it features zero friction and a more realistic behavior. For the buckling analysis, the bonded contact will be used as it acts as one part of the object to be analyzed. For the bolted fasteners, virtual connectors will be used as it saves time and computing resources. One major assumption for the material model is that the force distribution will be uniform over the surface contact, while the material used for the test structure will be ideally perfect, which is in homogeneous isotropic. On the right shows the meshing of the test stand structure subjected for analysis. Next is the material modeling for the base frame and the truss adapter. From here, we can see that three materials are chosen for the test frame. The AISI 1045 is a medium carbon steel, while the 6061 and the 7005 are aluminum alloy with high strength to weight ratio. The only difference is that the 7005 aluminum alloy is slightly better in performance. With the variations of material and also the thrust loading setting, the analysis is done where the results will be taken. For the static structural analysis, the circular hollow section is hypothesized as the weakest part of the thrust adapter. The maximum von Mises stress and the maximum displacement will be examined. On the right shows the contour results for the 6061 aluminum alloy, which includes the von Mises stress and also the displacement. From the contours, we can see that the von Mises stress at the circular hollow section is at higher concentration. The maximum von Mises equivalent stress is similar for the two aluminum alloys, along with higher maximum displacement compared to AISI 1045. Next is the buckling load analysis, where shell buckling and pure axial compressive load will be examined. From the results, it is seen that all of the material are below critical buckling load, and therefore the static structural results will be therefore evaluated. On the right shows the buckling modes examined for the 6061 aluminum alloy, which consists of 5 modes of buckling. Since all of the materials are under design conditions, as can see from the load factor, we move on to the final evaluation using the safety factor. The load factor derived from the results of the static structural test will be used for the evaluation, where the results is as tabulated here. From here, we can see that although the AISI 1045 has the higher safety factor, it is the heaviest material and therefore will be deemed as an over-design for the test structure. For the two aluminum alloys, the 6061 and the 7005 has almost similar performance. Although the latter has a slightly better performance, it has a higher cost for production and therefore will not be preferred. For the final conclusion, the 6061 aluminum alloy is deduced as the best material choice as it is safe for design loading as well as acceptable for extreme conditions. It is lightweight and therefore good for test portability and mobility. From the results of the analysis, it is examined that the stress magnitude and deformation are within acceptable limits, and the test stand structure does not have issues with the fasteners in the simulation. Therefore, that concludes my presentation today. I hope you enjoyed it and thank you.